What if millions of tons of broken glass, the kind we throw away every single day, could be transformed into something lighter than stone, yet strong enough to protect buildings from fire, water, and extreme temperatures? Around the world, glass waste is piling up at an alarming rate, filling landfills and polluting the environment, often with no second life in sight. But inside this massive recycling line, something extraordinary is happening. Through heat, pressure, and precise engineering, discarded glass is about to be reborn into a material that could shape the future of sustainable construction: foam glass. The journey begins with waste. Tons of discarded glass collected from households, factories, and demolition sites, all mixed together in chaotic piles of different colors, shapes, and compositions. But before any transformation can happen, this raw material must go through a critical stage of sorting and purification. Advanced systems and manual inspection work side by side to remove contaminants like metal, plastic, paper labels, and ceramic fragments that could compromise the final product. Only after this careful selection process, where precision matters at every step, can the clean glass fragments move forward into the next phase of production. At this stage, sorting becomes more than just a basic step. It is a precision-driven process that determines the quality of everything that follows. Advanced optical sensors scan the glass at high speed, separating it by color, density, and composition, while magnetic systems extract even the smallest traces of metal. In some cases, air jets are used to blow away lighter contaminants, ensuring that only pure glass remains. Even a tiny amount of impurity can affect how the material reacts under extreme heat, so every fragment is carefully inspected and filtered. What looks like a chaotic stream of broken glass is, in reality, being refined into a highly controlled and consistent raw material. Once purified, the glass is fed into powerful crushing machines that break it down again and again, reducing sharp fragments into fine uniform powder. This stage is more than just mechanical destruction. It is about creating consistency. The finer and more even the particles, the more controlled the transformation will be later in the process. What was once solid and rigid is now reduced to a soft, almost sand-like texture, forming the essential base material from which foam glass will emerge. Before the glass can be reduced into fine powder, it first goes through an initial stage of coarse crushing. Large fragments are fed into heavy-duty crushers, where they are broken down into smaller, more manageable pieces. The sound is sharp and relentless, as thick shards collide and fracture under immense force. This step is not about precision yet. It's about size reduction, turning bulky waste into uniform chunks that can be processed more efficiently in the next stage. By the end of this phase, what once were large, jagged pieces are transformed into smaller fragments, ready for a more refined and controlled grinding process. Once purified, the glass is fed into powerful crushing machines that break it down again and again, reducing sharp fragments into fine, uniform powder. This stage is more than just mechanical destruction. It is about creating consistency. The finer and more even the particles, the more controlled the transformation will be later in the process. What was once solid and rigid is now reduced to a soft, almost sand-like texture, forming the essential base material from which foam glass will emerge. At this point, the process shifts from mechanical to chemical. Carefully measured additives, known as foaming agents, are blended into the glass powder. These substances hold the key to the material's transformation, because under high temperatures, they release gases that will create countless microscopic bubbles. It is this hidden reaction that will give foam glass its unique internal structure, a network of sealed air pockets that dramatically reduce weight while enhancing insulation properties. The mixture is then transported into a high-temperature furnace, where the real transformation begins. As heat intensifies, the glass particles start to soften, slowly losing their rigid structure. At the same time, the foaming agents activate, releasing gases that become trapped within the viscous material. With nowhere to escape, these gases expand, pushing the softened glass outward and inflating it from within. The result is a dramatic expansion process, similar to dough rising in an oven, where dense glass evolves into a porous, lightweight structure. This is the exact moment when waste glass is reborn as foam glass. After expansion, the fragile structure must be stabilized through a carefully controlled cooling process. This stage is critical because any sudden temperature change could cause cracks or collapse the internal structure. By gradually reducing the heat, the material solidifies while preserving the countless air pockets formed during expansion. The result is a rigid, durable block that maintains its lightweight properties without sacrificing strength. In the final stage, the solid foam glass is cut and shaped into blocks, panels, or custom forms depending on its intended use. Each piece carries a unique combination of properties: lightweight, fire-resistant, waterproof, and highly insulating, making it ideal for modern construction and industrial applications. What began as discarded waste has now become a high-performance material, ready to serve in environments where both durability and efficiency are essential. What makes foam glass truly remarkable is not just how it's made, but how it performs in the real world. Despite its lightweight structure, it remains incredibly stable over time, resistant to fire, moisture, and even extreme temperature changes. Unlike many traditional insulation materials, it does not absorb water, it does not decay, and it does not release harmful substances. Its closed-cell structure locks air inside permanently, maintaining consistent thermal insulation for decades without losing effectiveness. In environments where durability, safety, and efficiency are critical, foam glass proves to be more than just a recycled material. It becomes a long-term solution. Because of these properties, foam glass is used in a wide range of demanding applications where both performance and reliability are essential. In construction, it serves as a high-performance insulation material for roofs, walls, and foundations, helping buildings maintain stable temperatures while reducing energy consumption. In industrial environments, it is often used to insulate pipelines, storage tanks, and underground systems, where resistance to moisture and extreme conditions is critical. It can even be found in infrastructure projects such as roads and railways, where its lightweight yet stable structure helps reduce load on weak soil. From modern architecture to heavy industry, foam glass quietly plays a role in making systems safer, more efficient, and more sustainable. In the end, what we're looking at is more than just a manufacturing process. It's a transformation, not only of material, but of perspective. What was once discarded as useless waste has been reshaped into something valuable, durable, and built to last for decades. Inside these massive machines, broken glass is not just recycled, it is redefined. And perhaps the most remarkable part is this: the future of sustainable materials isn't something far away. It's already happening, quietly in places like this, turning yesterday's waste into tomorrow's foundation.